the area formula of Green's theorem. So the area of D equals the double integral dA, which equals 1/2 of the integral of y dx plus x dy over the closed curve C. So before we use this area formula, we have to understand a little bit of what's going on, because we may have to use the RTs here, so we have to understand that component. So let's go back to the Green's theorem. So notice here we have the double integral of qx minus py equals dA. So if this is going to equal the double integral of dA, that tells us here that the partials qx minus py has to equal 1. Now, one other component of this, take a look at this original area formula here for Green's theorem. So let's take f equal to negative y comma x. And if I was going to use this formula here, then I would say that my qx is going to be 1 and my py is going to be negative 1. And then when I add those together, that qx minus, I should say subtract them, minus py, oops, that's going to equal 1 minus a negative 1, which equals 2. So when I look at this formula here, that's going to give me a 2 here. So what that tells me, if that's a 2 there, out here, I'm going to have a 1/2, so that when I multiply those together, I get the double integral of 1 dA. And that also tells me that this here, this negative y, is actually my p, and this x here is actually my q. And that's really what we need to see in this formula. What is my vector field in this? Because I'm going to need that in order to do some of my integrals. But I'm going to need it for all of the integrals dealing with the area using Green's theorem. And this is what my vector field will be. And when we take that step back to the previous one, notice our formula here, and that's where it comes from. But again, our P and our Q here is fixed when I'm dealing with this area formula. It's always going to be the negative y comma x. Now, understanding all of that, let's get back to our problem now. So for the following exercises, use Green's theorem to find the area. So that means we're going to find the area between the ellipse, which is x squared over 9 plus y squared over 4 equals 1, and the circle, x squared plus y squared equals 25. So that circle is of radius 5, that second one. The first one's an ellipse. So I'm going to draw these graphs here so you can see what they look like together. So the blue one here is the ellipse, and the red one here is the circle. And if we look at those together, we can see what's going on. Now, again, we're going to have to think of this in terms of, if we're going to use Green's theorem here, we have to think of the idea that we're cutting through one of the sides here to go around the inner one, just like we did previously. So not a big deal for us. So now what we're going to do is we're going to set up our integral for this, but we are going to need our RTs. I think one thing right away that we can see here is we can see that the area of the x squared plus y squared equaling 25 is, actually the radius is 5 there, so it's pi r squared. So that area is going to be 25 pi. And that's not the one we're really focused on here for Green's theorem. It's really this ellipse here that we're concerned about with that formula. So again, that area is going to be the area of the whole circle minus the inside. And that's the idea for this formula here. So first off, we have our f. And our f is, so again, with our f equaling negative y comma x, we can find our RT here. Now we're just looking at the ellipse. The other one we already know straight away. So the RT then is going to be 3 cosine t comma 2 sine t. And that's how the RT is going to work for the ellipse. So the radius on the cosine there is going to be 3, and the radius on the sine is going to be 2. And that tells me my distance from the center. It's very strange how that works, but try some points. Get comfortable with that idea there. And essentially now all I need is my x equals, 3 cosine t. And my dx then is going to equal -3 sine of t dt. And then for my y equals 2 sine of t. So then my dy is going to equal 2 cosine of t dt. So in essence, all we're going to do is just plug in all these components now. So for my double integral, and I'm just going to write double integral of dA here, just in general, so you can see the generalness of it. This is going to be 1/2. And my integral, dealing with my t being my theta in polar, that's going to run from 0 to 2 pi because I'm going all the way around here. So then I have my negative y. So my negative y is going to be -2 sine t. And that's going to be times my dx. And my dx is -3 sine t dt. And it's a times there. So then I have a plus, which is here. And then I have my x. So then my x is going to be 3 cosine t. And then my dy then is going to be 2 cos t dt. All right, so there's our setup here for this one. I should have moved it over just a little. Okay, there it all is. So now I can put all this together. So this is going to be 1/2 the integral from 0 to 2 pi. And this here is going to give me 6 sine squared t dt. But I'm going to pull the dt in the end there, so I'm not going to worry about it here. And then this component here, that 3 cos t times 2 cos t, is going to be plus 6 cosine squared t and dt on the end here. So if you hadn't noticed here, if I pull a 6 out here, I'm going to get sine squared t plus cosine squared t. And I know that this here equals 1, so it's really going to be a 6 times 1, which is 6. So that gives us, so we get that 1/2 the integral from 0 to 2 pi of 6 dt. And that's going to actually be the integral from 0 to 2 pi of 3 dt, which really is 3 t from 0 to 2 pi, which equals, I pull the 3 out here. And then inside I'm going to get 2 pi minus 0, which actually equals 6 pi. Now again, we just found the area of the inside, so in the ellipse here, using Green's theorem. And we know the area of a circle of radius 5, which is the other area there, and that's going to be pi r squared. So that's going to be 25 pi. So let's put this all together now. So on the bottom here, we have the 25 pi, and we have minus the area of the ellipse, which is 6 pi. So that's going to give us a total of 19 pi. So there's our answer for this problem here, finding the area using Green's theorem.